Okay, so chapter 15 is about solutions, and let's get into it. So aqueous solutions, and again, we've seen this aqueous symbol used before, this kind of AQ symbol. And a reminder that there is a difference between the symbol aqueous and the symbol liquid. Although they are both in the sort of liquid state, a liquid is usually a pure substance, like water, for example. So if you have water, that is a pure liquid. Aqueous, on the other hand, is basically a homogeneous mixture of two or more substances together. And it's basically a combination of two things. So if you took water, once again, that is a liquid, and you took some sodium chloride, which is a solid, the sodium chloride will dissolve in the liquid part. And those guys will then become a sodium chloride solution, and that guy would get the aqueous symbol next to it. Again, it's a homogeneous mixture where everybody retains their identity. Now, when we talk about a solution, there's two parts to a solution. There is the smaller part of the solution, which is known as the solute, and there's the larger part of the solution, which is known as the solvent. And our example up here, the water is our solvent, which is the larger part, and our sodium chloride here would be our solute in this case. The easy way to know which one's the solute versus the solvent is the name of the solution is what the solute typically is. So if you have a sodium chloride solution, sodium chloride is your solute. If you have a potassium chloride solution is your solute, and so forth. So really the name of this, bless you, the name of the solution is typically the solute. As we'll talk about here, and as we talked a little bit about in the previous chapter, those intermolecular forces, again, plays a really big role as to whether or not, for example, water is a good solvent. Water, as we'll talk about, is a good solvent for things that are polar and things that are ionic, but not a great solvent for things that are non-polar. So we'll get into that as well. So water, again, is, as I mentioned, really good for things that are polar and also ionic. When we dissolve something like sodium chloride in water, what happens is actually a type of intermolecular force that we didn't talk about last time or earlier today, but it is what is sometimes referred to as an ion dipole interaction. And what that means is we have ions, like the sodium ion, that's positively charged. And what happens when you dissolve it in something like water, the negative side of water, which is the oxygen, is attracted to that ion. So water will start to surround the positive ion through its oxygen, which again is that positive negative attraction. And when we have a negative ion, water works really well for those as well, because again, water also has a positive side. And the positive side of water is actually attracted to the negative ion. And this is what makes something dissolve in water, is this ion dipole interaction, this intermolecular force. And basically, that is why it appears that something like sodium chloride disappears. It doesn't really disappear. As we know, we can heat up the water and evaporate off the water and get the solid back. But what happens in this case is it just appears to disappear to our eye. And that's because we can no longer see it. There's just so many water molecules surrounding it that it sort of becomes not visible to our eye. And this is how something sort of dissolves. And this is why water is really good for things that are ionic, because it's able to do this and it's able to interact really well in that particular case. And that's what we see here. This process is sometimes referred to as hydration, where we kind of surround these ions with water. It really does sort of two things for you. It obviously helps it dissolve. It also keeps these two ions, which are super attracted to each other through electrostatic attraction. It keeps them apart. It almost buffers them out and they can't get to each other. And as I mentioned before, when we heat up something like this, all that water is going to evaporate. And if you did heat up this sodium chloride solution, Now there's really nothing in the way of these two ions coming back together. And that's why you will see the salt reappear at the end once you heat up the water and it evaporates off. And that's sort of that process. Obviously, when we do that process, this is an ionic solid, as we just talked about a little bit earlier as well. A very nice organized arrangement of those positive ions and negative ions together. And basically, water comes and plucks off these things because there's so many water molecules present, it's able to do so. You also help this along, usually, right? When you're trying to dissolve something, you stir it, which throws a lot of water molecules all over that solid and helps the process of it kind of coming apart from one another. And that's what we see here. Again, water molecules just kind of come in and pluck off some of those ions and then start to surround it.
An ionic solid dissolves in water because of its polar nature. Notice how water molecules become attached to the ions of a sodium chloride crystal in the process called hydration. Positively charged sodium ions attract the partial negative charge of the oxygen in water. A similar attraction occurs between negatively charged chloride ions and the hydrogen atoms, which have a partial positive charge. These interactions loosen the attractions between the ions in the crystal, dislodging them from the crystal. Additional water molecules surround the released ions, insulating them from attraction to other ions.
So as I said, it kind of does both things. It just helps with it dissolving, also helps keeping those ions apart from each other, where they definitely would want to get back there. So as we've been talking about throughout the different chapters, obviously we have two different types of bonding ionic sort of compounds, which again it results from a loss of electrons, creating a positive ion, which is a cation, and a negative ion, which is anion. Opposite attracts, again, intramolecular force. Covalent bonding, as we talked about, again, between two nonmetals, sharing of electrons, also intramolecular forces. Again, these are much stronger than those intermolecular forces that we talked about previously. Now, when we do get obviously nonmetals that share electrons differently, we get that polar bond. And as we talked a little bit about when we talked about hydrogen bonding, the presence of a polar bond can definitely increase the solubility of something. So that's very, very helpful. And we want to kind of get things to dissolve in each other to make a solution. And obviously, we can determine if it's going to be polar or non-polar, as we talked about in the previous chapter, by looking at the difference in electronegativity. And again, if we have a difference typically of above 0.4, it's going to result in some type of polar bond. And as we saw with our hydrogen bonding, we have a hydrogen that's attached again to a nitrogen, oxygen, or fluorine. Again, these being our most electronegative elements. And again, that's going to create a really good polar bond. So when we talk about solubility, what are some examples of solubility in water? Well, water again is pretty much your go-to for any ionic compound. Again, because we create positive ions and negative ions, that's going to work really well with what we just saw. They're able to do so. But again, there's also some non-ionic compounds that are going to be really soluble in water. And we touched upon one in the last chapter, but again, something like sugar or ethanol. Ethanol looks very much like our methanol that we saw in the previous chapter that we were talking about. Basically just has two carbons. But again, what sort of redeems ethanol's ability to interact well with water is the presence of that bond. And once again, when you look at ethanol, it's kind of a two-part molecule. This part here where we have carbons and hydrogens is nonpolar. But once again, because it has this sort of polar bond on it, it makes it very soluble in water, where the oxygen is more negative, the hydrogen is more positive. So once again, when a water molecule rolls up on it, it's able to interact again through hydrogen bonding, and it makes it really, really soluble in water. Something like sugar, which is a little bit bigger of a molecule, is very much helped by the fact that it has a lot of OHs all over it. So wherever there's an OH on sugar, even though it's a little bit larger of a molecule, it gives it an opportunity and a chance to interact well with water and hydrogen bond with water, which, as we know, sugar is very soluble in water. For that reason, it is loaded with it. By the way, solubility does start to decrease in these type of compounds, which are typically organic compounds, When you start to hit like 6 or more carbons, so if you had something like this, and all these were hydrogens and carbons, big giant guy here. And even if you had at the end here that OH group, because of this part of the molecule now is really large and nonpolar, it actually gets in the way of the ability of that little OH there to interact well with water. It is sometimes what you refer to in organic chemistry as steric hindrance. Basically, it's got this really giant nonpolar part just getting in the way, and it can't interact well with water. So something like that, even though it still has an OH group, actually has probably no solubility in water because of that really big nonpolar part of the molecule. So there are some things that can affect solubility, and that's one big one for example, organic compounds. If you got a lot of carbons and hydrogen, a really big nonpolar part to your molecule, it's just not going to work really well. And increasing, as we see with sugar, the amount of OH bonds that are present can also increase the solubility. So having a bigger nonpolar part kind of decreases the solubility in water. But if you have a molecule that has multiple OH groups on it, that's going to increase the solubility with water, again, because it's going to have an ability to interact there. So as we saw earlier, this is again our methanol hydrogen bonding with water, negative on the here and positive, positive and negative doing our hydrogen bonding between the water and the methanol. And there's our ethanol interaction that we just talked about. Once again, negative, positive, positive, and negative interacting there. Now, what about oil and water? Do they mix? Oil is insoluble in water, and they really don't mix for a couple of reasons. And one of the big reasons is oil is essentially nothing but just a long gold chain of carbons and hydrogens, basically. And as we've been talking about, carbon and carbon bond and carbon and hydrogen bond is nonpolar. So, what happens when oil and water try to mix? Oil, which is a giant nonpolar guy, is going to be rolling with those very weak dispersion forces that we talked about in the previous chapter. So if you remember, those are the weakest type of interaction you could have. And when water once again rolls around, it is going to want to use hydrogen bonding. And those are very, very different interactions. And they cannot maintain that interaction for a long period of time. So if you've ever seen an oil spill in the ocean or anything like that, the oil typically starts to float up on the surface of the water again because they will not mix with water and stuff like that. Um, the other really big thing is oil is typically very, very long, long chains of carbons together and hydrogens, and it just creates a really big molecule that is not able to interact well with water. So if you wanted to solve something in water, you essentially have to, before you do anything, break apart the water-water interactions. And what you're trying to do is replace water-water interactions with other interactions that are very similar to those. And when you're trying to do something with dispersion force and hydrogen bonding, they are very dissimilar. Plus, water is a very small molecule, and some big oil thing is a very, very big molecule. They really will not fit together really well. So you can think about like if you had a garage and you put a car in it, it's probably going to fit. But if you try to park a semi truck in your garage, it's probably not going to fit so well. It try to fit, but it's really not going to get in there very well. And that's sort of what happens here. So when we talk about solubility, one of the big things that people say, and one of the things that we sort of go with, is this idea of like dissolves like. And basically, what that means is if you want to mix two things together that's going to be soluble with each other, they're going to be able to mix all very well. You want both of those things to be using basically the same type of intermolecular forces. So if you put two things that hydrogen bond, they both hydrogen bond together, you're good to go. If you put something that dipoles together, they both do it, you're good to go. But if you try to do like we've been talking about here with oil and water, where somebody's using hydrogen bonding, somebody's using dispersion forces, you're going to run into a really big problem that they cannot do that. Why is that a really big problem? Well, dispersion forces rely upon kind of something happening, like we talked about, like the electron shift or something comes near it. Polar guys basically are good to go out of the box no matter what you do to it. As I mentioned earlier, they always have the positive, negative side to the molecule, which means they're always good to go in terms of bonding and ready to do these interactions. So when we talk about like dissolves like, basically what that means is if you're looking for something to be soluble and mix, anything that is ionic and polar, you should be good to go. Anything that is polar and you're mixing, you also should be good to go. And anything that is nonpolar and something that is nonpolar and you try to mix them together, you also should be good to go. So if you put those combinations together, they're all going to be using similar intermolecular forces, and that's going to make them all going to be really soluble with each other. You're only going to run into some problem and become sort of insoluble if you try to mix over something that is polar and nonpolar. You are not going to get those two to mix again for the reasons we've been talking about. So if you're evaluating a question or something like that, or you're trying to decide, should these two things mix? One of the first things to kind of help you with that is, am I dealing with a polar molecule or a nonpolar molecule and the polarity of it? And also, what type of intermolecular forces will each of these things be using? And again, if they're using similar ones, you should be good to go. If they're using very different type of forces, then you're not going to be good to go. Again, here on the left, ionic and polar is going to use ion-dipole interaction, which works well. Polar and polar will use hydrogen bonding or dipole-dipole. And nonpolar will use dispersion forces. So again, they will be all good to go there on the left-hand side where those guys are soluble. Here's a picture of sugar, which once again, although it's a little bit bigger of a molecule, you can see it is just littered with OH groups all around it. And once again, wherever those OH groups are, is going to give sugar an opportunity to interact well with water and become very soluble. On the very bottom, you might not be able to see, but maybe you can see it, is again our typical oil sort of molecule, just a long old chain of carbons and hydrogens, non-polar all day, not going to work well with water. When you do try to mix, again, oil and water, as we were talking about, typically they will separate out, and typically the top layer is the non-polar or oil sort of layer, and the bottom layer is the aqueous or water layer, where again we do have those hydrogen bonding. And that is typically what will happen. Again, if you took oil and vinegar salad dressing and you kind of mixed it, it will mix for a bit, because again, even something that is polar, like I said before, uh, can use dispersion forces, but they just can't maintain it because the oil is a very weak force, so they just can't stay locked into each other because there is going to be some difference in that separation of charge. So let's talk a little bit about solubility. When one item is soluble in another, that is what is said to be soluble. So if you take some sodium chloride and you mix it with water, sodium chloride is soluble in water. Most ionic compounds, again, are going to be soluble in water. When one substance does not dissolve in another, that is known as being insoluble. Oil, as we saw, is insoluble in water. There is usually a limit to the solubility of one substance in another. For example, there is a limit of solubility in something in water. So even though something is soluble in water, it is at for a specific temperature, and if the temperature changes, the solubility could change as well. And even at a specific temperature, at some point, you may add too much and it won't dissolve. So there is just a limit to how much you could get to dissolve. Now, there are things that are usually always soluble in each other. So gases are always soluble in other gases. And if you just think about gases, they are flying around. So just by that process, they are constantly mixing with each other. So gases should be always soluble in each other. Liquids are also soluble in each other. And again, as we just talked about, polar and polar guys are going to be good to go. Non-polar and non-polar liquids, which sometimes people overlook when they think about solubility, because again, they think like non-polar is not soluble in water. But remember that if you do have a non-polar molecule, it is perfectly going to be soluble in some other non-polar molecule that may be used as a solvent. So again, sometimes people just kind of miss that part of it. Um, in addition, when we talk about light dissolves light, there are some other factors that sometimes gets involved. The solubility of a solute does depend on temperature. Typically, if you raise the temperature, you could get a lot more solid to dissolve in a liquid. So if you just think about it, when you raise the temperature, you're increasing the overall energy. So that helps a lot in getting things to dissolve. When you lower the temperature, what happens is the solubility of a gas in a liquid also changes um, because you have a larger solubility of a gas in a liquid. So if you have a liquid and you have a gas molecule in the liquid, when you lower the temperature, the gas molecule is going to be flying around slower, which means as it's flying around, it's going to stay in the liquid part, dramatically drawn here, a lot longer than if it was a higher temperature before it exits. If it was a higher temperature, your gas molecules would be moving faster and then leave. Speaking of gases, there's also a dependency on pressure. And the higher the pressure, the larger the solubility, for example, of a gas in a liquid, right? Or just gases in general. If you remember Boyle's law, right? Pressure goes up, volume goes down, which means now you're in a small volume. You got all these gas molecules near each other, which means they're definitely going to be mixing a lot more because, frankly, they're just a lot closer to one another. Also works for a gas in a liquid under really high pressure. You have a lot more of the gas dissolved in the liquid portion. That is like your soda can example, right? Before you pop the top of your soda can, Henry's law, you have a lot more of the CO2 dissolved in your liquid part of your soda. When you pop the top, you release the pressure. A lot of the gas molecules could then escape. That's the fizzing you see come out the top, right? It's the CO2 basically leaving. Also, you gave it an escape route, which is not great because if you leave your soda can open for a while, you come back, you taste it, it tastes a lot flatter than it did right before. And that's because you gave it an escape route, and now that gas is less soluble and an escape route, so it's able to leave your can. And obviously, your soda is no longer as carbonated as it was before. Obviously, you popped the top and you left it open. Any questions on that there? Now, as I mentioned before, there is that limit to how much you could get to dissolve of a solute in a solvent. And what happens if you add too much solute to a solvent? You get a saturated solution. And a saturated solution is a solution where you have hit basically the maximum amount of solute that will dissolve for that particular temperature. So if you make a saturated solution, you basically have hit the point where that is the maximum amount of that solid that will dissolve. If you continue to add more solid to it, it will not dissolve anymore and it will just basically pile up on the bottom of your glass or wherever you're adding that to. So if you take a couple of sugar packets, right, and you put it in a glass of water, it's going to probably dissolve. You get the Costco size sugar, right, and you dump it all into a glass of water. Good luck on that. That's not going to all dissolve. At some point, it's going to stop dissolving once you hit that saturation point and you have a saturated solution. The opposite of that is an unsaturated solution. And in an unsaturated solution, you have not really hit that point yet. So you can still dissolve solid. And you can continue to dissolve solid in an unsaturated solution until you hit a saturated solution, basically. And at that point, it will stop dissolving. And again, you'll start to pile up on the bottom. Any questions on the difference between saturated and unsaturated? There is also a third type of solution, which is a supersaturated solution, which and there is a supersaturated solution. And what is a supersaturated solution? A supersaturated solution is a solution that is basically made this way. You typically will take something like a test tube or a beaker and you'll heat it up. And as you're heating it up, you will start to dissolve some solute in it to make a solution. So you'll start to dissolve some stuff. And because you're dissolving this as you're heating it up, what's going to happen is solubility again is based on temperature. So as the temperature increases, that's going to allow you to get a lot of solid to dissolve. You'll be able to get a lot more solid to dissolve in the solution than if you just did it at room temperature. So as you're heating it up, you're getting a lot of stuff to dissolve. And then what you do to it is you kind of stop heating it and you have a solution at this point, which is a supersaturated solution. And you typically let it cool back down. Now, what happens when it cools back down is this. The solubility at the hotter temperature is way higher than it now is at the lower temperature once it cools back down. The problem is you've already dissolved all that solid in there, so it's already dissolved. And now when it comes back down in terms of temperature, it's like you should not have all that stuff dissolved in me because we're at the wrong temperature for all that stuff that you just dissolved. So what happens is you get this solution that's actually has way too much solute dissolved at that given temperature. And because of that, it's a super unstable solution. It's so unstable that if you just took like you could barely see speck of whatever you dissolved in it and you just drop that one little small piece in there, it's going to go at this lower temperature. That's now way too much. And what's going to happen is going to go from a liquid state to you could actually start to see and will see all of the solid come out of solution. So it'll go from this liquid state, and then all of a sudden you'll start to see like all the solid come out of solution, and you will be left with like a rock hard solid at this point, basically, because it's very unstable. It is so unstable that when I've done this demonstration before, if you like knock the flask just a little too much, it could actually just cause it to do that without you adding anything. So it's very, very unstable because it ends up being a solution that has way too much solid basically dissolved in it. Any questions on that there? So we'll take a look at this video of it, and then we'll probably do it a little bit later on in the lab here, provided they make the solution. Hopefully, it's made. Let's see. So here's an example of that supersaturated solution.
The flask contains a supersaturated solution of sodium acetate in water. A small crystal of sodium acetate will be added to the solution.
So the solution that you saw was made how I described. Basically, they dissolved a bunch of sodium acetate, this stuff, in water. They heated it up as they were doing it. So they got a lot of solid in that liquid right now. And they now let that solution cool back down. They're going to take one little drop or crystal of the sodium acetate and put it in there.
Your attention on the portion of the solution to which the crystal is added.
Yeah, that's right. You can barely even see it. And then now you can see just by adding that one little speck of it, that is now going from a liquid to a rock hard solid. All the solid is just coming out of the solution. And now that you can bang that thing, probably not, and it will not do anything. It's a solid at this point.
Here is the process again in slow motion.
So this again is a supersaturated solution. And like I said, it's typically a very unstable solution because it just has, once you let it cool back down and make it, and now has just too much dissolved in it. And it wants to kind of correct that problem. And any little disturbance will allow it to do so. Let's talk about some other ways that we describe solutions. Solutions can also be described as concentrated. And in a concentrated solution, you have a relatively large amount of solute dissolved. In a dilute solution, you have a relatively small amount of solute dissolved. Classic example is you hit like the AM PM before you hit class, you get your drink from the Thirst Oasis with all the ice in it, and you drink it and it tastes really good, right? And it tastes like it should. And then you go to class and you leave your drink in your car and you come back and all the ice is melted, but you're thirsty, so you go, how bad could it taste? So you give it a taste, right? And then maybe you regret it afterwards. I don't know. But it doesn't taste as good at that point, right? Because all that ice melted and you just diluted it down with a lot more water, right? So it's not as strong as a much more dilute solution. Typically in the lab, we get solutions in a more concentrated solution, and then we dilute it down in terms of its concentration to a much not as strong solution. All right. So let's talk a little bit about some concentration units. And the first type of concentration unit we're going to talk about is mass percent. It is sometimes abbreviated percent M/M for mass percent. And the mass percent is I'll just write it a little higher so it's easier to see in this room. The percent M/M is the mass of the solute divided by the mass of the solution times 100%. So this is like grams divided by grams in this case, and times 100%. The important part of this calculation or formula is actually the bottom part. And remember, as we talked about earlier, the solution is made up of two things. It is made up of the solute plus the solvent. So you definitely want to make sure that you have both of those values. And the reason I say that is very commonly in textbooks and stuff like that, in these type of questions, they will oftentimes separate those two numbers. They'll tell you the mass of the solute and they'll tell you the mass of the solvent kind of separate from each other. And it's a very common mistake that people make, which is they just kind of roll with the solvent because it's a larger number and they put that on the bottom rather than adding them together to get that. So you do want to make sure that you have both of those sort of values added together to get the total mass of the solution. If you had a 4.5% by mass sodium chloride solution, you can convert that into like a conversion factor and do some dimensional analysis. What that would mean is you would have 4.5 grams of sodium chloride and 100 grams of solution. So you could kind of use that as a conversion factor. Just like it's a conversion factor, you could flip it around and go 100 grams of solution gives you 4.5 grams of sodium chloride. So sometimes in these problems, it's easier to maybe take it as a dimensional analysis approach rather than using the formula. And again, a reminder that if you do some dimensional analysis calculations, you sometimes don't even have to remember these formulas. Just think about what you want to get rid of, what you want to keep in terms of units, and it will kind of do the formula for you and the rearranging of the formulas for you. But this is a very good way to turn a percentage into a usable sort of unit. Now, there are a couple of other sort of concentration units, and once again, I'll write them a little bit higher so we can see them. Percent volume to volume, and that is the volume of the solute over the volume of the solution times 100%. And then we also have percent mass to volume, and that is the mass of the solute over the volume of solution times 100%. It is basically, this guy is basically milliliters over milliliters. This one over here is grams per milliliter, kind of like density is how we use these. Again, on any of these sort of percent concentration units, you could plug and chug into the formula, or you could do a conversion factor. So if you had a 4.5% by volume, which is what they use for like alcohol of sodium chloride, that would mean you would have 4.5 milliliters of sodium chloride in 100 milliliters of solution. or you could flip it around. 100 milliliters of solution would give you 4.5 milliliters of sodium chloride. So once again, if you want to take a more kind of conversion factor approach and you're given the percentage, you could do so. And same thing if we had something like 4.5% mass to volume sodium chloride solution, you would have 4.5 grams of sodium chloride and 100 milliliters of solution. Or you could flip it around. 100 milliliters of solution would contain 4.50 grams of sodium chloride. So they all sort of work the same. Unlike percent mass to mass, you don't really have to worry too much about the volume here on the bottom of the solution. Usually, I would say in problems, they kind of give you the volume of the solution. They don't really break it out into solute or solvent. They could, but most of the time they don't. But really, on that mass percent, you do want to be careful of sort of the mass of the solution. Any questions on those three percentages there? All right. Let's take a look at one. Why don't you take a moment here? A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of calcium chloride. So we're looking again in this case, percent. Okay, let's take a look. So again, we're going to do percent mass to mass. And that again is our mass of our solute. It's a smaller part of the solution divided by the mass of the solution times 100%. So in this case, we got 2.5 grams of calcium chloride. And that is going to be our solute, as that is the smaller part. Our 50 grams of water here is going to be our solvent. So once again, the larger part of the solution. And we're looking for the mass percent. So we do want to add those together to get us 52.5 grams is actually the mass of the solution in this case. So again, we don't want to just divide by 50. That is just the solvent. We want to make sure we get them both. So our percent mass to mass is going to be 2.5 grams divided by 52.5 grams times 100%. And that's going to get us here 4.76%, I believe. Now, the way you could typically leave it is just write percent M/M, and you can put calcium chloride if you like. That is sort of the way the answer is sort of given. Any questions on that? Like I said before, in these type of problems, very common. They separate out both the solute and the solvent in terms of the information. And again, you definitely want to make sure you get them both, not just the solvent. Any questions on that one there? All right, then we'll try another one here. Concentrated hydrochloric acid solution contains 37.2% by mass. What is the mass of HCl that's contained in 35.5 grams of the concentrated hydrochloric acid solution? Take a few moments, see what you come up with here. Okay, so let's take a look. Once again, we're dealing with mass percent, so we could use our formula here. Now, you could definitely plug and chug into there. You also could, if you wanted to, because you were given the mass percent, you could turn this into a conversion factor and take a more dimensional analysis approach. How do I know I'm looking for the mass of the solute? Again, the name of the solution is the hydrochloric acid solution, and we're looking for how much hydrochloric acid we have. So that tells us that we are looking for the solute in this case. So if I were to kind of turn this into a usable sort of conversion factor, that would mean I have 37.2 grams of hydrochloric acid in 100 grams of solution. Once again, I could flip it around and put it up on top and use it as a conversion factor in this form. 100 grams of solution is 37.2 grams of HCl. Since I know my mass of my solution, I could just go dimensional analysis here, 35.5 grams of solution. I got to go opposite to cancel. So again, without even thinking about the formula, I don't have to rearrange it or figure out, what to kind of use. I could just take that dimensional analysis approach. And like normal, we know what we're doing math-wise. We're multiplying and dividing. So our grams of solution cancel. And that's going to end up giving us 35.5 times 37.2 divided by 100, about 13.2 grams of HCl in this particular case. Again, that is the same if you rearrange this equation. You're basically doing the exact same math. The mass of the solute in this case will equal the percent mass to mass times the mass of the solution divided by 100%. So again, that's basically the same math as what we just did. Any questions on that one there? Okay. All right, so we talked a little bit about these percent concentrations. Let's really talk about the most common concentration unit for solution, and that is molarity. And molarity, I would say, is definitely your biggest concentration unit or the most common one. Molarity is abbreviated with a capital M, and it does stand for moles per liter. More specifically, it stands for moles of solute per liter of solution. And you should think of molarity really as a formula because you are asked to solve for any one of those three things. Sometimes you're asked to solve for the molarity, sometimes you're asked to solve for the moles, and sometimes you're asked to solve for the liters or volume. So, kind of like density, you could rearrange it similar. Liters would be moles divided by molarity. And if you want moles, which is a very common use, liters times molarity is the way that you rearrange that. So, like I said, any one of those three things is very, very common to use. Now, other common conversions that pop up when you're using molarity is our typical grams to moles conversion using the molar mass from the periodic table. That again is a conversion factor that's used a lot with molarity. Other ones I would say for sure is most of the time when we take measurements of volume, it's in milliliters and it needs to be in liters when you're using molarity. So your 1,000 milliliters is 1 liter conversion is used a lot with molarity as well. The bigger the number for molarity, the more strong and concentrated of a solution there is. So if you grab 18 molar hydrochloric acid, that is super strong versus 0.01 molar hydrochloric acid. So when you look at the bottles of reagents that we use, they usually have like a little number with an M next to it. The higher that number is, the stronger the solution is. Now, when you're doing calculations and you do have the molarity given to you in a problem, or you're going to use the molarity in a calculation, I 100% would recommend to you that you get rid of the big M. And what I mean by that is if you're given something like you have 4.5 molar sodium chloride solution, when you go to do the calculation, you should get rid of this M and convert it into really like a conversion factor of 4.50 moles per 1 liter. And again, you could use it as a conversion factor and flip it around and put the liters up on top, 4.50 moles. The number always goes with the moles part, and the liters is always one. So the liters part is always one when you have the molarity. The number always stays with it. Why do I tell people to do that? Because I can't tell you how many people's papers I've seen when they do a calculation involving molarity and they have no clue that there's even a volume there. They just think M, oh, it's moles. And that's all they think is moles because they see M. And it's not. So it is moles per liter. If you see both units and convert it into this, in a calculation, you should at least be able to see, hey, there is liters and understand what you're doing. And if you take, again, a more dimensional analysis approach to the calculation, you may not even have to worry about rearranging the molarity equation. Again, it will kind of do it for you. But you definitely want to be able to see those units along the way. You do not want to multiply milliliters times molarity. If you take milliliters times molarity, you do not get what you think you get a lot of times when people do that. You do not get moles. You get what are known as millimoles, which means if you think they're moles, you're going to be off by like a factor of 1,000 on your calculations. So you can multiply milliliters times molarity, but you get millimoles and not moles. So again, most of the time you need moles. So again, make sure that it definitely is liters there. That way you will get moles at the end of it, and that's probably what you need for your calculation. But you will see sometimes people will do milliliters times molarity, but that does give them millimoles rather than moles. So as we talk about, if we do have a solution, and I'll just kind of write it a little bit higher so what's on the page, so if you can kind of see it. If you had a 1 molar solution of sodium chloride, as I mentioned, what that means before is you basically have 1 mole per liter of sodium chloride. Now, what that means is you have a mole of sodium chloride dissolved in enough water to make 1 liter of solution. But something like sodium chloride, when you have a sodium chloride solution, is a strong electrolyte. If you remember, we talked about electrolytes, and something that is a strong electrolyte will 100% break apart in solution, which means if you technically have sodium chloride solution, you will have 100% sodium ions floating around and chloride ions floating around. So if you had a beaker of sodium chloride solution, that is all you have basically floating around in there. By the way, they are surrounded by water, like we talked about earlier on in this chapter or the previous chapter. And they're floating around. You have none of these sodium chloride whole units sealed together. So it's 100% over here, these guys. Now, how does molarity work if you're interested perhaps in just the ions concentration rather than the whole thing? It works just like stoichiometry, which means this is a 1-to-1 relationship between the whole thing and the sodium ions. How that affects the molarity for the sodium is you would take 1 times the molarity, and the concentration of sodium ions that are in that solution would be 1 molar. It works the same way for the chloride. It's a 1-to-1 relationship, which means in terms of the concentration, you would take 1 times the 1 molar for the whole thing. And that would give you that it is 1 molar chloride ions in that solution. Now, what happens if you did not have a 1-to-1? Say you had calcium hydroxide. That's going to break apart into a calcium ion and 2 hydroxide ions in this case. Say 2-for-1 special on that deal. Yeah, you get twice the hydroxide than you do the calcium in this case. How that affects concentration of molarity is when you look at just the calcium ions, it is a 1-to-1 relationship, which means it is 1 times 1 molar. It is 1 molar calcium ions in there. But when we look at the whole thing, which is 1, to our hydroxide, it is a 1-to-2 relationship, which means you got to take 2 times the concentration of the whole thing. And this thing would be 2 molar hydroxide ions floating around in there. If you just think about it in terms of your beaker, for every 1 calcium hydroxide you drop in there, you're going to get 1 ion floating around of calcium and 2 ions of hydroxide. There's twice as much hydroxide for every calcium. So the molarity is twice as much for the hydroxide that it is for the calcium in this case. So the quick way to figure out the molarity of just an ion, if you're interested in that, is if it breaks apart into a 1-to-1, it'll be the same concentration. 1-to-2, multiply the concentration by 2. 1-to-3, multiplied by 3. 1-to-4, multiplied by 4. Why is it that? That is the shortcut calculation for the long version of it, which is if you took our 1 mole per liter of calcium hydroxide which is what 1 molar stands for. And you do your mole to mole relationship. 1 mole of calcium hydroxide gives me 2 moles of hydroxide. The moles of calcium hydroxide cancel. We're going to multiply by 2, and that's going to give us our 2 moles per liter of hydroxide, which is what this concentration is. So it really is just multiplying by the mole to mole relationship, but the quick way, again, is just to multiply it by the coefficient. So this doesn't happen all the time, but sometimes, especially with ionic compounds, because the ions are floating around freely in the solution, we're sometimes interested in what the concentration of just the ions are rather than the whole thing. So that does happen occasionally, that you need to kind of relate the whole thing to just the individual ions. Any questions on that there? All right. All right, so let's take a look at an example here of molarity. We want to calculate the molarity of a solution that's prepared by dissolving 15.6 grams of potassium bromide in enough water to make 1.25 liters. So potassium from the periodic table there, 3910, I believe. And bromine from the periodic table, 7990. All right, so take a moment here. We are looking for the molarity of this solution. Okay, so we are looking for molarity, which is moles per liter. We don't have moles, but we can get to moles from the grams. So that is one thing that we need to do. In this case, our volume is actually in liters. So we actually have that good to go right there from that. So the first thing we want to do in this case is actually calculate the moles of KBr. So we're just going to add these two together, and that's going to give us 119 grams per mole. That comes from obviously the periodic table. Remember, that is our conversion factor to convert our grams into moles. So we'll divide by 119 grams per mole of KBr. Again, the grams are going to cancel as we multiply and divide here. And we're going to end up with 15.6 divided by 119. That's going to give us 0.131 moles of KBr. At that point, we now have the top part that we need. So we got top part and the bottom part. So we could calculate our molarity by taking our moles that we just calculated, divided by our volume, which is in liters. Again, if it was in milliliters, you would need to convert it to liters. And we're going to divide it by 1.25. That's going to give us a 0.105. Now, in terms of the units of how you can leave the answer, you can leave it in one of two ways. Since the units do not cancel, the mole stays with the number and is per 1 liter, and you could call this KBr. The other way you could give your answer is at this point, you could put the big M back in, and you could give it as 0.105 big M KBr. So either one is acceptable in this case. Any questions on that calculation there? Okay. All right, let's take a look at another one here. What is the mass in grams of sodium nitrate that is required to make a 2.5 liter solution of 0.15 molar sodium nitrate? Sodium from the periodic table, 2299. Nitrogen 1401, and oxygen 16. So we're looking for how many grams to make 2.5 liters of a 0.15 molar solution of sodium nitrate. We do know molarity is involved, so we think about molarity, which is moles per liter. And what you want to think about is, do you have anything here? So clearly I have my volume here. Once again, it is in liters, and if it wasn't in or if it was in milliliters, you would have to do the conversion. So I do have my liters. I do have the molarity given to me, so I have that. So the only thing I really don't have at this point is moles, which makes a good idea. That's probably a good place to start, because ultimately we're looking for grams, and I know I could do moles to grams using the molar mass. So again, you could rearrange the molarity equation here and solve for moles, which is liters times molarity. Once again, if you don't want to worry about sort of the equation and rearranging the equation, because you are given the molarity, you could use it as a conversion factor. So once again, because you're given 0.15 molar solution, that means that is 0.15 moles per liter of sodium nitrate, and you could use it as a conversion factor like so. You could also flip it around and use it like this. So what that means is at this point, I don't really have to worry about the equation. I know I have liters and I want to get rid of liters. So I could just do my opposites cancel, which means I will use my molarity in this form where I can see both of the units there. So now when I multiply and divide, the liters will cancel. And once again, this is why you do need the volume in liters. Otherwise, if it was in milliliters, not going to cancel correctly. You're going to end up with here 2.5 times 0.15. That's going to be 0.375 moles of sodium nitrate. Now, 0.375 moles of sodium nitrate is great, except that if I wanted to go weigh this out, like you will do in this experiment, you probably want how many grams it is. So at this point, we can now use the moles to get to grams, and that is NO3, NaNO3. So that's a 2299 plus a 1401 plus 3 times 16 here for the molar mass from the periodic table. That's going to get us for sodium nitrate here a molar mass of about 85 grams per mole. That again is going to be our conversion factor. Opposites cancel, so we do want the moles on the bottom. That way the moles will cancel when we multiply and divide. And 0.375 divided by 85. I'm not divided. 0.375 times 85. That might be better. It's going to be about 31.9 grams of sodium nitrate. First off, any questions on that calculation? That number means that if you went to the balance and you weighed out 31.9 grams of sodium nitrate and you use enough water to dissolve it and end up with a volume of 2.5 liters, once you mix that together, you will have a solution that has a molarity of 0.15. So if you were going to make this solution like the lab would want you to do, you would weigh out your grams, you would add your 2.5 liters of water, you would get all the mix together, and you will end up with a 0.15 molar solution at that point. Any questions on that there? All right, we are going to lay it up there.